Okay, thank you for comments. I will be talking about hacking traffic control system from US and a few other countries. So this is quickly about me, just to make a point that I'm not new in the security business industry. I have been around for a long time. Have been doing different kind of research, and this is my last research. And I didn't want to leave the thanks to the end because I got a lot of help from different people, most from my company. And maybe it was little help, but when you put everything together, it's a lot of help, and it allows you to save a lot of time. How this research started? Well, I always was curious when you go in the road, in the street, in a highway. If you look around at the poles, to the electronic signs, at the toll collector, at the traffic light, you will see a lot of different devices. Most common are the traffic signals, and besides that, the cameras, the traffic cameras. But if you pay attention, you will find a lot more different devices around. So I was really curious about that, and I wanted to research some of them, and I didn't know anything about that. So I started to look around. And when I was looking around, I found some news that the Department of Transport from London was going to implement some traffic wireless detection system, and it got my attention because London is a big city, important city, and these devices are wireless, so it's an interesting technology and possible attack vector if they are insecure. So I started to look around specifically for this technology. It took me a while to find out the vendor because they were acquiring the devices from a reseller, so I keep digging, and I found out that the vendor name, the maker, and it was really interesting because when I keep searching, I found out that it was really widely deployed, mostly on the US, but also in a few more countries. So this is information from the customer. They say they have more than 250 customers worldwide. Customer will be like city, the Department of Transport, state, the Department of Transport, or the country could be. And in the latest news from the vendor, I saw they state that they have 200,000 wireless sensors deployed worldwide. Most of them are in the US. Here you can see, this is an image from the vendor, the deployment around the US. You can see most important cities are there, maybe it's small for this screen, but most important cities are there, including Las Vegas. For instance, one popular deployment is Washington, D.C. This is a slide from a vendor presentation. So they say there are 1,300 wireless sensors installed there in Washington, D.C. When you start to research, you get the available documentation, and I found kind of user manual, a 100-page user manual, and it has just one paragraph about security. So that was a really good indicator that probably these devices weren't really secure. So there was a challenge how to get the devices because these devices is not something that you can easily buy around because customers are probably resellers and governments. So what we did was social engineering the vendor, saying that we need to do some testing for an undisclosed customer, and we need just a couple of devices, which is weird because when they get bugged, they get by the dozen or hundreds. So after some talks, they agreed. So we got a couple of devices, and at that time I was in Puerto Rico, so I got them shipped to Puerto Rico, then came to the US with the devices, then returned to Argentina, then returned to the US, to Argentina, to the US, to Argentina, like 5 times with the devices without any problems. The point is that you can freely travel around with these devices without any problem. So what are the devices? Well, first we have the wireless sensor, which I have one here. You can see this small device. So this goes in the road. So basically they are magnetometers. So they detect the anomaly in the natural magnetic field of the Earth. In that way, it can detect when a car goes over it. So in order to install it, you had to make a hole in the road, put the sensor, and then it's filled with epoxy. So the battery life is 10 years. This is what the vendor says. And it has a Texas Instruments radio transceiver, which is CC2430, which is pretty common for the H102.15.4 specification. It runs on 2.4 gigahertz. And it also has a microcontroller from Texas Instruments too, which is the MCP430, which is also pretty common. So I lost my initial note, but I think they run TinyOS. So this is like a view of how internally is the sensor. You have in the top there is the antenna. So below is the electronic board, then the batteries, and then the plastic that is around protecting it. So we open it, and there you can see the antenna at the top. Here we push out the electronic board, and there are the batteries. This is the board, and here you have the transceiver, the microcontroller, and then the devices, electronic devices used for detecting the magneto interference. Then we have the access point, which is this white box. You can see here. You can usually find this in a pole next to the traffic lights, or sometime in another pole around. So basically what the access point does is get the wireless data from the sensor, from the traffic detection, and relays it to the traffic control systems. It runs using Linux. It has a Cold5 processor, and also runs software, and it interfaces with the traffic controller with a contact closure card in order to communicate with the traffic control systems. It can be used as a router, etc., in internet networks. Then we have repeaters. I don't have one of that, but it's similar to the access point. It's a white box. And basically what it does is to extend the range when the sensors are too far away from the access point. So they transmit on two different channels. In one channel, they get the information from the sensors, and in the other channel, they relay the data to the access point. So this is the range for the communication between the sensors and the access point, which is a maximum 150 feet. Then if you want to extend the range, you have the repeaters, and the maximum range by vendor documentation is 1,000 feet. But of course, I mean, if you have equipment, antenna, you can probably go further away. How these devices work? Well, like I said, the sensor goes in the road. There are different implementations, different configurations. One of those is this one at an intersection. So here you have several sensors that are used for stop bar detection. Means that once a car is stopping, they are waiting for the signal, the sensor will detect it. Then you have advanced detection to detect when the cars keep coming and are being waiting also far away from the stop bar. So the sensor get the detection data and send it to the access point, and the access point relays it to the traffic control systems. So basically, the traffic control system uses this information to know how to best set the timing, for instance, for the green light. If they see in this direction there is a lot of traffic, they will set the timing longer. If it was 10 seconds, it will make it maybe 20 or 30 seconds. Depends on the configuration. Also, at some intersections, probably most of you or some of you have seen this at late night. Sometimes you are waiting at an intersection and the traffic light won't change or will take a lot to change. That's sometimes because the detection mechanism is not working very well. So that's the stop bar detection. So when a car is waiting, the traffic control system will set some parameters so that the traffic light can change faster and you get the green light and you can go. This is how the access point connects to the traffic controller by a contact closure card. Also can connect to some internal network, etc. Another deployment, another configuration is on RAM meters. For RAM metering, sorry. So here you have present detection, which is kind of stop bar detection. It will detect when a car is waiting, and also queue detectors to measure the length of the queue. Then, at the freeway, you have several wireless sensors to measuring the traffic that is in the freeway just before the ramp, the access ramp to the freeway. So in this way, the traffic control system knows how to set the proper timing to the RAM meter. If they see there is no traffic at the freeway, they will turn off maybe the RAM meter or will allow the cars go faster in the freeway. If there is a lot of traffic, they will allow the cars go slower in the freeway. Another kind of use is for travel times. So basically, you get an array of sensors at some point in the freeway, and then maybe 1 or 2 miles away, another array of sensors. What they can do with this technology is to uniquely identify a car. So basically, they detect the car, they do some post-processing, and they will create a fingerprint of the car. So after a mile or 2, they will re-identify the car so they can know what's the travel time for that lane. So that information is the information that you later see on the electronic signals on the freeway. And also, it can adjust the speed limits. If they see there is a very low speed at some lane, they could lower down the speed limit. So in order to configure the devices, to access them, there is a Windows software that basically is built with Adobe Air. So it's actually script, Flash. It's very easy to decompile. You get the source code. You get there the hard-coded root credential for the access point, but that's a local attack vector for the internal network, so I didn't go that way. And so you connect to the access point with this software, and then you can access the sensors too. And you can configure them, install, update firmware, etc. Then you have some server software that you can use to concentrate, to collect all the information from different access points, different intersections, etc. And also the vendor provides a software as a service solution that allows you to connect to any access point worldwide and look at some information and set some specific configuration options. But I didn't test this because this is server side, and will be, of course, illegal. So this is a diagram how the information from the access point goes to a central location sometimes, and then it's distributed with the different traffic control system of a city or some place. So what are the vulnerabilities I found? So basically, they don't have any encryption. So all the wireless communication is clear text. This was interesting because it took me a while to make this thing work because I don't know if it wasn't built correctly, but it took me a while. But when I make it work, I saw that there was no encryption. And when I reported these vulnerabilities through ICS CERT, I got information back from the vendor saying that they do use encryption, but I didn't saw it. So they were claiming that, yes, they were doing encryption. And the only paragraph I mentioned earlier that I found in the user documentation was the next one. So you can read it there. So basically they say because the ready transmission don't carry any commands, it's only data. There is like, it doesn't care because there is an opportunity to attack. That was what I understand, because it's really difficult to understand what they try to say there. But that's the only paragraph about security in the whole user manual. So when I continue insisting that I wasn't seeing any encryption option in any place, that I wasn't looking at the communication, there was no encryption, they get back after many emails with this answer. You can read it. Right, it's funny because the customers are governments, so I don't know if intentional or it's just a lie from the vendor because the vendor was lying all the time, but it's a really crazy answer, right? Because it works as designed, so there is no issue there. So other issue is that there is no authentication. So nothing prevents an attacker to access a sensor or to access a repeater. I mean, access points are protected because you have to access them through the internal network, but sensors and repeaters can be accessed wirelessly, and there is no protection mechanism. Also, the access point doesn't authenticate the sensor nor the repeater. So access point get any data that match the protocol and that match the address of the sensors, and they will just accept that data as trusted. Sorry. So another issue is that the firmware updates are not signed, not encrypted at all. So basically, you can go and change the firmware of the sensor and of the repeaters. So when I told all of this to the vendor, this is from a presentation from the vendor. When I was looking at different documentation, I found a presentation and say, okay, this proprietary protocol, so it's hacker safe. But what they said to me when I reported the issue was that they were encrypting, signing the firmware in the next version of the sensor. But what's the problem? The problem is that these sensors are buried in the road worldwide. So because the security architecture is non-existent, how would you update the firmware with encryption in a secure way without actually changing the sensor physically? I mean, you are open to attack because you have to share the key in some way. So basically, they will have to do a physical replacement to have a secure update of this. But well, so let's see about the protocol they use. So basically, it's the standard 802.15.4 physical level. It's the same that Zigbee and other wireless protocol you use. It's very low data rate, because they choose this because it's very low power consumption. And it has 16 channels on 2.4 gigahertz. And they have their own protocol, which is the Sensys Nano Power Protocol, which is kind of a media access protocol. Basically, it's a customization of the MAC standard. It's very similar, and it's used TDMA. So they divide the time frame in 64 slots. So the access point will tell to one sensor, okay, you have to transmit and listen at this time, and so on with every sensor. They do that to avoid collisions and also to optimize the power consumption so the sensor doesn't need to be awake all the time. So sensors will only listen and transmit at some specific time slot, but the access point will get data at any time. I mean, you can just send data to the access point and it will get it and process it. So if there is no detection, so there is any car around, then the sensor will just send a status information every 30 seconds. The access point just acknowledges when they get detection data from the sensor. If there is no acknowledged, then the sensor will retransmit a few times and then will get to sleep. So a basic packet structure is the following. So the first 2 bytes are for the kind of packet. Then the other byte, the third byte, is for the sequence number, for the sequence of packets in this transmission. And the following 2 bytes are for the address of the sensor, because the sensors are identified by these 2 bytes. So the access point knows from where the data is coming. And then it's the data part. So the frame header is for the type of packet, as we can see. And then there is a special, in the address part, from the access point side, they use a special byte which they call color code, which is used so the sensors can know if they are getting information from the right access point. Because the access point doesn't have a specific address, the sensors will know that they are getting the right information by this byte, the color code, by the radio channel and the color code. So the data part is 4 to 50 bytes. So the data that the sensor sends is sometimes the battery level, the firmware version, the detection of the car, if there is traffic or not, and then from the access point to the sensors or repeater, you get synchronization data, and also configuration information, and also firmware updates. So this is a sample packet from the sensor to the access point. That means there is no detection on any event. So basically, it's what they transmit every 30 seconds. And this is a slightly different packet, which means there is a detection of a car. This is also from the sensor to the access point when they send status information and configuration information. Sometimes you can query the sensors with the access point to know how they are configured. So here they send the firmware version, the channel, the physical address that they get from factory that you can change. So they will send all this information. And finally, this is a sample packet from the access point to the sensor that is used to synchronize the sensor when they say, okay, you transmit in this timing and you on this other timing, etc. So for the firmware, they provide the firmware in a file which has a proprietary format that looks this way. So the first 2 bytes are the address for the flash memory, I think. They have the firmware twice. I think they do it because when the firmware is actually running in the device, it's running at some specific address. So when it gets the update, it will copy it to the alternate address, which is specified here. If it's running at the first address, it will copy the firmware update to the other address, and then we reboot and change. So basically, the security mechanisms, or I don't know, it's just one checksum at the end of each line, which is XOR, very simple checksum. And then you have a general checksum for all the firmware, which is 8 byte, which is also kind of XOR. So basically, you change the firmware, you modify it, and then generate the checksum, and that's it. Then you can update it. The packet for the firmware update is very simple. You just upload the firmware to the access point, set the sensors in firmware update mode, and then the firmware is start to be broadcasted by the access point. So basically, they broadcast every line of the file. You can see here the file. Okay, now I have that's the file. It's just one line, as you can see there, and that it was its broadcasted. So in order to do this research, I needed some hardware because you have to sniff the wireless communication, then you have to be able to modify packets and modify packets, etc. So basically, I got a USB dongle for sniffing the 802.15.4 protocol, which is this device, very small. You can see it here. It's pretty cool. You just plug it, and it will start sniffing with the software provided. And then I got a programming board, all from Texas Instruments. So you get the programming board, you get the radio transceiver, the antenna, and also a sniffer. Just plug the programming board by USB to the computer, and then you have the framework to program it, which is the IAR, Embedded Workbench, IDE. And then the Smart RF Studio and the packet sniffer software. We can see the software. This is for sniffing. So you can see, just run the program, and it will start getting the packets. These are the packets from the access point to the sensor. Here you can see the data. And if you know the protocol, you know it's clear text because all the information is just there, the address and the options. So it's pretty simple. Just look at the setup, the type of protocol you want to capture, and then set up the radio channel here and start sniffing. And then with the testing board, you have the RF Studio, which is pretty cool. You just choose the radio transceiver, and you can manually craft packets and send them. You can also sniff packets too, which is really cool because you just type the packets, the complete packet, and you can just send 1 or 100. It's very useful for testing. And finally, the software for programming the device, you just code it in C, and then it will upload the firmware, and you can debug and test. It's pretty simple. So what's the impact? So the vendor says there are 200,000 sensors worldwide. Most of them are in the US. I would say, based on my research, maybe 80% or 70% are in the US. And then you have repeaters also. I have seen the prices of the sensors. Each sensor is $500, $600. The access point is $4,000, and the repeaters are 1,000 or more. So we are talking about 100 million or more worth of equipment that probably can be bricked. So you can see there is a huge money impact here. Then, of course, you can cause traffic jams because you can directly influence the traffic control system, because you can lie to the system. You can send fake data and say, okay, there is a lot of traffic here and there isn't any traffic, or maybe there isn't any traffic and there is a lot of traffic. So you can cause a big mess in the traffic. I don't remember exactly how many years ago there was a conflict with the Los Angeles Department of Transport over the transport traffic engineers, and a couple of them hacked, I don't know if it was 2 or 4 intersections, but they were the main intersections of Los Angeles, and they created a chaos for 2 days, just hacking 2 or 4 intersections. So, because you know, when there is a problem at an intersection, it propagates over the other intersections. And if they are the main of the city, then you have a big mess. Also, of course, it depends on the configuration of the traffic light or the traffic controller, because they can have different configurations. So you can have simple accidents or really tragical accident, because you know, when people see that it's waiting at a red light and the red light doesn't change and you are there 1 minute, okay, 1 minute is fine. 2 minutes just no so fine. And more than 2 minutes, the cars will try to go anyways. And in that way, you get accidents. So what the US Department of Transportation says, they say that sensor malfunctions and associated signal failures increase motorist time and delay, maintenance costs, accidents, and liability. This is what the US DOT says. It's not me. So I have an issue with the vendor, because all the communication was through ICS CERT, and what I get back from the vendor was lies, because I was saying, okay, there is no encryption, and they came back saying, yes, there is. I said, there is no authentication. They came back and said, yes, there is. So they were lying or saying really stupid things. So I had a conflict because I did the testing at home with these devices, which is a non-production system. So I don't like to make a statement saying, okay, these devices are insecure, and maybe when you go to a production site, you see that the configuration is completely different, or maybe they have another options, and what you found is completely inaccurate. So what I did was getting the devices in my backpack. I make them portable because the access point is by default is powered over Ethernet. So I got help and make it powered over USB, so I can connect it to a portable battery supply. And then I connected it to a portable Wi-Fi router. So I put the access point in my backpack, and then I could access wirelessly the access point from my notebook. So I went to Seattle, New York, but the problem that in Seattle, when I tested, was a testing site. It wasn't a production site, so I wasn't very sure. The same on New York, but when I went to DC, which is a big deployment there, it was a production site. So I did some testing there that I will show you now. So this is New York. It was cool because I was just next to the New York police traffic. So here you can see the marks from the sensors in the street. Those black round circles are the marks. And then in the pole, here is the access point. And this is just like 3 blocks away from the Empire State. So there I basically was pointing with my backpack to the sensors because it's a directional antenna. So I was pointing with my backpack to the sensor, and I was able to access the sensor. I was able to see the configuration of them. And if I wanted, I could have compromised them, changed the firmware, which I didn't do it, just in case. So there is, we see this later, is the software from the vendor. So I put the access point in discovery mode, which they query for sensors some specific channel. So the sensor started to appear in the graphical interface. There is a line, you can see green. That's my sensor, which I had also in my backpack. But then it started to appear a couple more. There you can see 3 more sensors. that were there in the road. And see, I can find the okay, doesn't matter. I just wanted to show that it was like 5 blocks from the Empire State. So I went to DC, and DC just when we get out the Union Station, we found a nice surprise because I didn't know there was something there. So I was looking around just outside the Union Station. I think it's a ramp exit ramp. And we found some sensors there. There you can see the mark of a sensor, because maybe if you have been there, that is a really complex intersection. There are, I don't know how many streets there. And there you can see the access point. So that configuration is for detecting that a car is waiting there at the ramp trying to exit, so it will put faster the green light, or if they don't detect any car, they won't get any green light. So I was, you can see, pointing my backpack to the sensors. And there, I was able to access them, just to look at the configuration. Basically, it's capturing the wireless data and displaying it in a graphical interface. But because the software knows how to process the data and give it meaning, I can see all the options, the configuration options, etc. So that is the traffic I was seeing from the access point to the sensor and to the sensor, from the sensor to the access point. But there is another part. We went to do some testing. We had a lot of sensors there, and there was a repeater too. Here you can see every line is a sensor except one, which is a repeater. There are the sensor, and this one is the repeater. So just clicking in one, I can access them, change the configuration if I want, change the firmware, do anything, change the channel, the radio channel. And this was, as you can see, 2 blocks from the Capitol. I mean, there was some weird people, some spooks, but we didn't get any problems. It was weird. We weren't paranoid because we weren't doing anything illegal, but it was weird. There was the access point, and here in the street are the marks from the sensors, and there was a repeater here. So in this way, I could prove that I was right with what I was saying, what I found. So what are the possible attacks? So basically you can do denial of service, which is not cool. So you can disable the sensors, change the frequency channel, change the firmware, probably brick them, send fake packets. But the cool attack will be send fake traffic detection data, because if you know how the protocol works, how the device communicates, you can just send fake data. And in order to do that, I built a special device I will show you later. So basically you just send fake data saying, okay, there is a lot of traffic here, but there isn't, etc. What I already said. So in order to launch an attack in a real world, it's kind of easy because there is a lot of vendor presentation, documentation, press releases where they say, okay, we are implementing this in New York, in DC. There is a lot of public documents also from the government. And the cool part is you can specifically know the coordinates of the devices using Google Street View. Here are a couple of repeaters, and here are the sensors. This is New York. So you know specifically the GPS coordinate where they are located. So this is really cool for an attack. So basically, on vendor specification, you had to be at least 1,000 feet away in order to attack them, to be able to connect. So one option to attack is being on site, so being near the devices so you can send fake data. So what I did was building this, which I programmed a sample, a proof of concept, which is cheap and dirty proof of concept. I can show you here. We see in the other side. So basically, simple, you have a LCD screen, so you can put a menu there. So I put a menu to different attacks. One is from creating fake sensors or replacing existing sensors. The other one is to send fake data. I did some ASCII art. Maybe you can see. And then I also can send fake data about configuration. I will show you now. So I have here the vendor software. So I will connect to the. I'm connected to the access point now. So basically, here in every line, you get the devices, which are the sensors and repeaters listed there. So you can see there isn't any device there. So there is just one, which is my sensor I have. So now I will create fake sensor. In a real attack, it will be replacing existing one, maybe disabling them or just sending fake data. So I will push this button here, and you will see the sensors being created. So you can see I'm sending fake data to the access point, and the access point is parsing the data and accepting it as a valid data. And there is a couple of interesting columns here. One is the present, which means that a car is present at the sensor, and the other is the number of detections, which is number of cars being detected. So now what I will do is send fake data about car detection, about traffic. So I push now, and you will see here the detection number to be increased a lot. So basically, the access point is taking this data, which is fake, is made up, as valid and processing it. So this is the data that will get the traffic control system to take decisions. So if you don't want to be on site, what you can do is just to program a radio transceiver tube with a GPS when you set up the coordinates of where the devices are located and attach it to a bus or to a car or to a coast, and just let it go. Because on DC you have the map where the buses go, so you can know where to launch the attack automatically by the device attached to the bus. Another option which I tested and works is from the sky by using a drone. This is a new service where you can rent drones if you don't have. So you basically, in my test, I attached this to my drone, make it float like 650 feet and launch the attack, and it worked. And so when you have line of sight and you have a good antenna, you can go 1,000 feet or more on the sky and launch the attack. Another attack could be to do a firmware update worm. So basically, you change the firmware and make a worm, so it will propagate itself, infecting the sensors that are near. Or maybe not near, because the repeaters will propagate the worm too. What is cool is when you have the firmware compromised, there is no way to know if it is compromised or not unless you dump it and you look at the code and see there is something weird. But if you just use the functionality, you never know if it is compromised or not. For this kind of crazy attack, maybe future, is basically you can know in real time using social media, GPS coordinates on pictures, etc., where people is. So you can search maybe in Foursquare, people in New York at this right now, and then you could compromise their smartphone, and from the smartphone launch an attack. Right now, I think it's kind of limited, but if we are talking about software-defined radio, or maybe a radio that can be modified also by using this protocol, you can have someone else with his cell phone attacking these devices. And another kind of crazy attack, this is based on immunity, guys, not my idea. It's basically because you can fingerprint cars, you can use this as a trigger to a bomb. So you fingerprint one car, and then use that fingerprint to re-identify later a car at some intersection, at some place, and use that as a trigger to a bomb. So because this is in Washington, D.C., maybe you can fingerprint Cadillac One. So the final conclusion is like any serial work guy like me, you know, I live in a small town, like many miles away from here, can get these devices that are used on critical infrastructure in the US and other countries and hack them, and then if you want, hack the US or other countries. The attack tool, it will cost you $100 or less to build it if you buy the part and program it. It's cheap. Something that we are seeing is crazy. It's like the government is buying devices that are being used in critical infrastructure without testing the security of them. They are just assuming the crazy claims from the vendors, and they are putting it on critical infrastructure. That is happening right now. And finally, when we talk about the smart city concept, where the city gets smarter to take decisions, if you get devices like these that blindly trust the data, then the city is not very smart. It's kind of stupid. And finally, cyberwar is cheap. So I'm part of Build It Securely. We are trying to help small vendors to improve the security of Internet of Things devices. So if you don't know about this, you can check the site, and there is nice step-by-step instruction on how to build secure products, etc. And that's it. I hope you like it.